All right, thanks very much. This is Calling Functions Across Languages. I'm Richard Feldman. So something that I've run into many times in my career is finding myself doing some programming and thinking, this task that I'm doing right now would be a lot easier if I could use another language. Like one reason might be, maybe I want a library that's in a different language from the one that I'm using. Maybe I want more performance that I can get out of the language I'm using. Or maybe I'm using a language that's really low level and I actually want something higher level with sort of better ergonomics, even at the potential cost of speed. Or maybe I just want to transition between two languages. Like I want to call a function in another language just because I'm trying to transition to that one and I don't want to have to rewrite my whole code base all in one go. So a good experience that I've had with calling functions across languages reminds me of a time when I used to do Scala. So if I was in Scala and I happened to want to call a function in Java, it was super easy. There was syntax for it. I could just import the Java function and just call it right away. Another time that I've done some calling functions across languages is I used to do JavaScript code and I worked at a company that had a Ruby backend. And so we called Ruby functions from JavaScript, over HTTP. But it's still calling the functions. The logic was written in Ruby, and we were getting the answer in JavaScript. Here's another one that I've heard of. I haven't personally used, but NumPy, the library for doing linear algebra, among other things, in Python, actually for its linear algebra stuff uses under the hood inside this library Fortran, which is a programming language from 1957, originally done on punch cards, which I assume they're doing using sorcery. I mean, how is that even possible to have a library that calls code from another language from half a century ago in the same library? But we're going to actually get into how it does that. It turns out it's actually not sorcery. But of course, this is sort of necessary if you want to do performance. Like there's no way that they're going to be having NumPy to say, hey, we want these really highly optimized linear algebra routines. And the way we're going to access them is over HTTP, over the network. Of course, that's going to be way too slow. So of course, they're not going to do that. So what are they doing? Well, to get there, let's start by imagining this hypothetical function called dot product. It's a linear algebra function. Don't worry about what it does. I actually don't know what it does. It's going to be fine. But the point is that it takes two arrays of numbers and then it returns a number. And what we're going to do is we're going to start by sort of with this JavaScript calling Ruby over HTTP. So dot product's going to be implemented in Ruby and JavaScript's going to call it over HTTP. And then one at a time, we're going to sort of peel back the layers of abstraction until we get all the way down to calling the function as directly as we can. Okay, so first let's just peel back one layer of abstraction and say, let's start with an HTTP request. And that's basically consists of two parts. One is we build the HTTP request string, and the second is we take that string and send it to a socket, and then the operating system will send it across the network. So let's see what that looks like. So we'll start with this in JavaScript. Now, JavaScript, if you're running it in the browser, doesn't actually let you go directly to sockets unless you're doing WebSockets, which is kind of a different thing. So we're going to use Node.js here, but let's start with just looking at what's the actual string that's going to get sent to the socket. So it looks something like this. If you haven't seen an HTTP request, it's basically a string that says get, and then the path that you're going to get. So in this case, we're going to say /.product. So that's going to be on the Ruby server. Then you say host. We're going to do localhost for this example, because first rule of calling stuff over the network is that if you want to go fast, don't actually use the real network. Just go to localhost on your same machine. Got some sort of boilerplate HTTP header stuff. And then finally, we have the actual data that we want. I've put this in JSON format here. These are the actual numbers that we're going to send to the dot product written in Ruby. So over on Ruby, we're going to have this implementation. It'll be Ruby, they call it a method. So it'll be a method called dot product, takes two arrays, A and B. These JSON arrays of numbers are going to end up getting passed into there. And then Ruby's going to say, okay, I'm going to give you back an HTTP response, which looks something like this. Again, some more boilerplate. And finally, the number, which is the answer to this, 70, or at least so I'm told when I put this into some other program, because I don't actually know what a dot product does. Anyway, so this is what happens, right? JavaScript builds the HTTP request. It's got the arguments in there. Ruby receives those arguments, deserializes them from JSON, makes the response, calls dot product, actually gets the response, then makes the response and sends it back over the network to JavaScript. Okay, so what does the sending it to the socket part look like? Well, again, in the browser, we can't really do this. So I'm going to use Node.js for this. So in Node.js, if you want to make a socket, you say const socket equals new net.socket. You basically connect to localhost port 3000. And then we say request string is just, we're going to have some function that builds this HTTP request saying it's a get. Here's our path. Here are the headers. Here's the body, which is JSON.stringify, our two arrays that we want to give to Ruby. And then finally, socket.write, which takes that request string that we built up and then writes it out to the socket. And that socket's going to go over localhost port 3000 over to Ruby, which is then going to deserialize the arguments from the socket and then serialize the answer to the socket after it's computed it. So Ruby, here's the sort of equivalent on the Ruby side. Again, doing this sort of the manual way. So TCP server.new, localhost port 3000. In Ruby, you do a loop to have it sort of listen for connections. Server.accept says it should wait for new connections. Parse the HTTP request. It gets all the headers and all that good stuff out of there coming from the client. Then we do JSON.parse on the body of that to get array 1 and array 2. These give us the two arguments that we're actually going to pass to our method. Hey, finally, we're actually doing the dot product. Everything up till now has just been overhead, but finally, we're going to really run this dot product function. This is the thing that we actually wanted to do, passing in array 1 and array 2 and getting our answer. And then, of course, there's a little bit more overhead because we have to turn that back into JSON, send it back across to JavaScript, and then close the connection. Whew, okay, finally, we did it. Wow. All right. So that was a lot, but we did successfully do it. We peeled back one layer of abstraction, and we've seen what it takes to, over HTTP, send a request from JavaScript to Ruby, and then Ruby sends the answer back. All of that is just sort of wrapping around what we actually want, which is to run this dot product. All right. So we can see all this overhead, but really, ultimately, this is all we really want, is we want to send these numbers over to Ruby, and then Ruby does some math on them, and then returns back this other number as an answer. So how can we sort of strip away some of this stuff? Well, the first thing that comes to mind is all this HTTP boilerplate. We don't need all that if all we need is really the actual numbers involved here. So let's do that. So we're going to build this HTTP request string, send it to the socket. And here, I'm just going to take what we've done when we've peeled back one layer of abstraction. I'm just going to remove some of this general HTTP boilerplate stuff. And we're just going to say, you know what? I'm just going to do the JSON part where I turn the arguments into JSON and just send that straight to the socket. Now, granted, this means that now our socket, like port 3000 localhost, can only do one thing, which is the dot product. But never mind that. We've gotten rid of some overhead here, and we're no longer doing all the HTTP boilerplate around that. Same thing on the Ruby side. Now that HTTP stuff's gone, we don't need to deal with it anymore, and we're just sort of dealing with the JSON parsing, reading directly what comes off of the socket, and then sending more JSON directly back over the socket. Cool. So we eliminated some of that overhead. That's nice. This JSON part, though, of course, JSON is not the most compact way to represent numbers. If we use the binary encoding rather than JSON, we could make it even more compact. So let's say we just had some sort of serialize, deserialize. Who cares exactly what the details are? But point being, it's a way to encode this that let's assume is more compact than JSON. Okay, eliminate some more overhead there. Also, we're still using a TCP server, which has some overhead of its own. We could eliminate some of that by using a Unix socket instead. For example, if we're on a Unix system, Windows has an equivalent to this. And basically, this is like, rather than setting up sort of a real server, you use this file as a way to communicate between two different processes. So we've got our Node.js process and our Ruby process running on the same machine. If we know that we're going off localhost, we might as well use something that's a little bit overhead, like a Unix socket. By the way, at this point, we're doing what's known as inter-process communication, or IPC. So you can now, because we've sort of peeled back the layer of abstraction one step at a time, you can kind of see if I was doing inter-process communication, there's actually a lot of similarities to this and doing an HTTP request. It's just like the actual HTTP string stuff is sort of what goes out the window. At the end of the day, there's just not that much difference conceptually on what we're doing when we're talking between two processes versus talking between a client and a server. Okay, if you're interested in inter-process communication, by the way, there's a cool paper here about sort of different benchmarks of performing different tasks and seeing which approaches to inter-process communication are faster than others. So here it's comparing pipes, shared memory, and sockets. This is basically graphing the latency, which they're measuring as the time between when the sender sends the information and when the recipient, that is the other process, receives it. And then they're graphing this based on message size. So you can see, of course, as message size goes up, latency goes up. It takes longer to send more bytes. That makes sense. But also you can see that there are different approaches that have different trade-offs and can be faster or slower. So here's sockets in the blue on top. This is what we were doing. This actually has the highest latency of any of these three approaches. But beyond the other two, between shared memory and sockets, it actually depends on the message size, which one's faster. So if your message sizes are under 8 kilobytes, then actually it turns out that pipes are the fastest. We're not going to get into exactly what pipes are, how they work, but that's something that would be faster for something like really small, like what we're sending, these really small messages. But as soon as you get over 8K, it actually switches and shared memory becomes the fastest. Now, a downside of shared memory is this is something you can only do if you've got a parent process that spawns the child process. You can't have two sort of arbitrary disconnected processes communicating over shared memory. So lots of trade-offs here, but point is there's ways we can make this inter-process communication thing go even faster by sort of switching it up from sockets to something else. Okay, so zooming out a little bit, the goal was we want to call this Ruby function from JavaScript, and the way that we did this at first over HTTP was serialize this serialize this data as JSON, the URL, the headers, the request body, the JSON, all of that stuff, send it over HTTP to Ruby, which then deserializes the request, then does the actual work and serializes the response back, adds the headers and the body, and then JavaScript deserializes the response. So we made that a little bit faster by saying, okay, let's just talk to localhost rather than going over the network. And then also we can kind of, instead of going to and from a TCP socket, we can sort of generalize this using inter-process communication and say, well, if we know we're going to the same machine, then we don't have to use JSON specifically. We can just do a binary encoding. We can make all this stuff a little bit faster by removing some of the HTTP overhead and stuff like that. But fundamentally, we still do have two different processes. We still do have a lot of serialization overhead and communication overhead here. And really, at the end of the day, if we want to get this as fast as possible, we really want to do this inside a single process. Like we want to have a actual function call. JavaScript just calls Ruby, and that's it. So how do we get down to this, where we got JavaScript, and we're like, well, I just want to run the dot product function. I don't want to do all this inter-process communication stuff, let alone network stuff. How do I actually do that? Because that is going to give us the lowest overhead that we can possibly get. It's just calling the function across the language directly. Okay, well, to answer that question, let's think about what actually is going on in a process. Well, at the end of the day, a process is lots of ones and zeros. The end. Thank you for coming to my talk. Just kidding. So there's, of course, a lot more going on in there. There are a bunch of ones and zeros. And in fact, literally, if you were to look at an executable binary on your disk, this is what you would see, a bunch of ones and zeros. Now, you probably would not see these exact ones and zeros because I just made these up by typing 1 and 0 into my keyboard over and over. So I don't actually know what happens when you run this, but I wouldn't recommend it. Having said that, that is, at the end of the day, if you open up any executable binary on your disk that any program you've ever run, it's just a bunch of ones and zeros. So the question is, what's actually going on in those ones and zeros? So let's unwrap that a second by pretending that instead of ones and zeros, it's JSON. So let's pretend that instead of a bunch of ones and zeros, what you actually had on your disk is a JSON array that started off with, let's say, a string that says, add the next 2 entries, followed by a couple of numbers like 42 and 123. And you can imagine when the computer comes along, it's going to read that instruction and somehow it knows that magical string, add next 2 entries means take the next 2 entries in our JSON array and add them together. And then maybe it hits another instruction like add the next entry to the answer that we've got building up so far. So 42 plus 123, and then we would add another 200 onto that. And then maybe the next instruction is jump to the index in the next entry in this JSON array, which maybe there's a 3 in there next. And so it says, okay, well, if you just add numbers along the side for the indices of each array entry, it says, oh, I see. At index 3, that was this add next entry to answer. So, replaying the whole thing, it's basically we start off with this instruction, add the next 2 entries, so 42 plus 123. Then we add the next entry to the answer, which is 200. And then we jump to the following index, which is 3. At index 3, we've now done a goto. Hey, we've done a goto index 3, at which point we're adding the next entry to answer again. So now 42 plus 123 plus 200 again. And then we're going to come back to the jump, which is going to jump back there. And we've created our first infinite loop. Fantastic. Okay, so this is just going to keep jumping back and keep doing that loop around, adding 200 over and over again until it runs out of memory. But the point is that conceptually, this is actually quite similar to what's happening on your CPU. So you have all of these instructions that the CPU understands. It has these sort of low-level primitive operations that it knows how to do, things like adding the next 2 entries in the binary, perhaps, among other things. Some of them are like load this memory, load that memory, do this thing, do that thing. But they're not, of course, actual JSON. That would be a very inefficient way to encode all of this. What they actually are is they're numbers. So, for example, instead of saying add the next 2 entries as a string, it'll be like the number 5. And that's hard-coded to be add the next 2 entries in the list, this sort of magic constant number. And when I say hard-coded, I don't actually mean in software. I mean in hardware. Like inside your CPU, there is some wiring or some circuitry that says the number 5 means add the next 2 entries in these sequence of instructions. Like that's what that means somewhere. It's not, I don't know if it's actually 5, I just made that up, but the point is there are these things called opcodes, which are just numbers that represent these instructions. So 5 might be the opcode for add the next 2 things. Let's say there's another one that's like add the next entry that's 17. Again, I'm making these up. You can actually look up and read what these opcodes really are. Jump to the index, the next one, let's say that's opcode 29. So how do we get from here to ones and zeros? Well, at this point, once you have it in the form where it's just all a bunch of numbers. Numbers can be encoded in binary as ones and zeros. Like the ones and zeros encoding for 5 is this. For 42 and 123, it's this. For 17, it's this, yada, yada, yada. And now we can actually see like literally what's going on when you have a binary full of ones and zeros. This is it. Like this is all it is. It's a series of instructions that are just encoded in this really compact form that the CPU is hardwired to understand what those instructions mean. And that's how you get a binary. Cool. Okay. How can we use that to call functions across languages? Well, imagine I've got an executable binary where I've put some JavaScript code in there and some Ruby code in there. Well, at the end of the day, what is JavaScript code? What is Ruby code? Like what is actually running in there? Well, basically, at the end of the day, they're ones and zeros, right? There's some code in here that says, I know how to do JavaScript-y stuff. And there's some code in there that says, I know how to do Ruby stuff. And yeah, they might be reading files off the disk, but at the end of the day, it's JavaScript flavored ones and zeros and Ruby flavored ones and zeros. And there's absolutely nothing stopping me from putting the two of those inside the same executable so that they'll run the same process. I can just totally do that. It's all ones and zeros. So, okay, but then like literally how do you go from running JavaScript code to actually running Ruby code? Well, essentially it's, let's say these bytes represent a jump, right? We just jump. Instead of jumping to, index 3 like we did earlier, which was earlier in our own code, you can jump ahead and jump to ones and zeros that haven't happened yet. For example, we could jump into Ruby code and just say, cool, now we're executing Ruby instructions. And then somewhere in the Ruby instructions, there's a jump back to where we came from. That's totally something we can do. Now, this is a little bit risky. There are some pitfalls with doing this, to say the least. Let's explore that a little bit. So let's go back to our sort of JSON mental model of this, because that's a lot easier to read than ones and zeros for humans. Add next two entries, add next entry to answer, jump to index and next. So here we have the integer constant 42, right? The whole point of my storing 42 in there is I want to add it to 123, and that's totally something I can do. Now, here we also have a memory address. This is something that says jump back to index 3. Now, the thing is, there's no type information associated with this that the CPU sees. The CPU, when it's coming through, it's just like ones and zeros. So there's ones and zeros representing 42, cool. There's ones and zeros representing 3, cool. It doesn't see these as conceptually different. It's just like, whatever ones and zeros you put there, that's what I'm doing. So let's give an example of where this might go wrong, specifically when calling JavaScript and Ruby. So let's say we had an instruction that says basically like, I'm going to load the next entry and we're going to use that as our array length. So let's say I've got an array with 4 things in it, like our numbers that we're using for dot product, for example. And we're going to say, yeah, let's load the length of the array because we're going to iterate over it. That's something that we do in dot products is we iterate over the arrays. And of course, in order to know when to stop iterating, we have to know what the length is. So we've got this array length of 4, no problem, store it in there. And then we're going to have an instruction that starts iterating based on that length of 4. Okay, so here's what the number 4 looks like in JavaScript. If you were like, hey, JavaScript, give me a number 4. These are the ones and zeros that JavaScript's going to put in there. Notice there's like the bottom 3 rows are all zeros, and then the top row, it's got a couple of ones in there. Now, here's the problem. This is what Ruby does. If you say, what's the number 4 in Ruby? Ruby uses a totally different set of ones and zeros to represent the number 4 than JavaScript does. In Ruby, the top 3 rows are all zeros, and then there's a single 1 in the bottom row. Okay, so how could this cause things to go wrong? Well, let's say we've stored our array length in JavaScript because we're starting in JavaScript, and we're like, hey, Ruby, here's my array. Here's what the length is. And JavaScript's like, oh, here's the ones and zeros representing array, the array length. And we just jump over into Ruby land, and then Ruby interprets those same ones and zeros. So JavaScript has put these there and said, we're jumping into Ruby land. Ruby's like, oh, cool. I see these ones and zeros. This is our array length. What length does Ruby think this is? I'll give you a hint. It's not 4. No points for guessing this because it's a very large number. This is what Ruby thinks the length of your array is if you do this. And then because the CPU is just like ones and zeros, got it, chief. It's going to be like, oh, this is how many times you want to iterate through this array. You got it. And it's just going to start going and going and going. And of course, it's going to read way off the end of the array in the memory. And then all sorts of bad things are going to happen. Hopefully, you'll get a segmentation fault, but it could be a lot worse than that. It could like corrupting memory, doing all sorts of stuff. Basically, gigantic explosion. So the consequences of getting this wrong and just sort of being like, oh yeah, it's no problem. We'll just like just be going along in JavaScript bytes, and then we'll just jump into Ruby bytes, and everything will be fine. Well, there's lots of ways that it could very much not be fine if you make a mistake. Okay, so we don't want to just do this naively. What do we want to do instead? Because we have our JavaScript bytes, we have our Ruby bytes, and we want to jump between the two so that we can actually call a Ruby function from JavaScript in the same process. So literally, how do we do that? Well, basically, the conceptual idea is that we're going to translate before we jump. So specifically, we're going to start by reading the JavaScript bytes and then using them to make some Ruby-shaped bytes, whether that's a number, or as was the case in our array length example, or it could be the arrays themselves. Those are also represented differently in JavaScript and Ruby. Whatever they are, we're just going to say, okay, we've got our JavaScript stuff. We're going to create the Ruby equivalents of those before we jump. Then we're going to jump to the Ruby instructions so that Ruby can actually use those Ruby-shaped bytes, which is what it knows how to do without exploding. And then finally, once Ruby's done, we're going to take the Ruby-shaped answer that we've got and then use it to make a JavaScript-shaped answer, at which point JavaScript can run. Now, you might notice there's actually a little bit of similarity here between what we were doing previously with all of our JSON serialization and deserialization. There is still some conversion that's happening here. It's just that we're doing it at a much lower level. We're doing it at the level of individual ones and zeros in memory, rather than having to sort of package all this up into a completely different format, an intermediary format, send it across the wire and all that stuff. So this is sort of a lower overhead version of the translation we were doing previously using JSON and then later some other binary format. Okay, so to sum up, what we need is some way to read arbitrary bytes and write other arbitrary bytes in memory, because that's how we're going to put these things in place so that when we do the jump, it works. And then we need some language that will do that for us. But JavaScript and Ruby are not very good. I wonder what language we could possibly do to make this work out a little bit better. Now, actually, there are several languages we could do. I know Andrew Kelly's in the audience, so I'm going to mention that Zig is actually an excellent language for doing this. But in this example, because I think more people know C than Zig, I'm going to use C as our example. So what we don't want to do now, if we're using C to put these bytes in the right place, what we absolutely do not want to do is to painstakingly figure out exactly what bytes need to go where in JavaScript and Ruby by hand and just be like, oh yes, we'll just handcraft these artisanal bytes and bits and ones and zeros, and we'll surely never make a mistake that causes everything to explode, because we will totally make a mistake that causes everything to explode. So we don't want to do that. But fortunately, we don't have to, because other people on the internet have made functions that will convert, not in this case, directly between JavaScript and Ruby, but what they have given us is, in this case, this is the Node.js Node API, which is basically provides things to convert from C types to Node types, and then also functions to go the other way around from Node types to C types. So now we can go to and from Node.js and JavaScript. JavaScript and C via Node.js. So if I've got my Node.js stuff, I can convert it to and from C representations in memory. I can get the ones and zeros that C expects from the ones and zeros that JavaScript expects, and vice versa. That doesn't get us quite to Ruby. Fortunately, Ruby's got the same equivalent. So here's the sort of similar thing for Ruby. This is basically a way to convert a Ruby value into C, and then also to convert a C value into Ruby. So putting those two together, if we've got inside the same process, Node.js stuff that we can convert to and from C using C, and Ruby that we can convert to and from C, well, guess what? Once it's converted to C, C knows how to talk to C without any conversions. So basically what we can do is put those together and have a way to call a Ruby function from Node.js by using C as an intermediary. So we start by converting the ones and zeros in Node flavor to C flavor, and then we convert it from C flavor into Ruby flavor, and then back the other way. So again, kind of similarly to what we were doing previously, except rather than doing it with JSON or something like that, we're using C as our intermediate representation to go between these two. Okay, so let's do it. Here we have our, let's assume we have our dot product method implemented in Ruby. Not actually going to write that out. Then we're going to call it from Node.js. And the way that we're going to do that, it's going to look something like this. So import dot product from Ruby linear algebra. And this just looks like essentially a normal Node.js import. It's actually the same syntactical thing that we had in this Scala example, trying to call Java. We're literally just importing this thing directly, even though it's written in a totally different language. Now, we're going to see in a second that there's some behind-the-scenes glue taking place that's going to make this happen. But it is pretty cool that we get this user experience. I didn't have to set up a whole socket, let alone HTTP requests. I'm just import it, done. I can just now call it directly, which is what I wanted the entire time. So ergonomically, nice. This is great. And also, it doesn't have the overheads of inter-process communication or the network. Okay, so how do we actually implement the bindings between Ruby and Node? Well, let's look at that. So we're going to start with, this is some C code. We're going to include node API.h. This is the C to Node.js library that I showed you earlier. And here we're going to include Ruby.h, which is the Ruby one between C and Ruby that I showed you earlier. And then basically we're going to start writing some C code. So here we're going to say, if you don't know C, don't worry about it. I'm just going to kind of conceptually go through what this is doing and hand wave a lot of implementation details. Static NAPI value dot product basically says we're defining a function called dot product. And when we're done, there's some boilerplate that I'm not going to show that will basically tell Node.js, hey, use this compiled C output as an actual Node.js module. And so we're going to name it dot product because that's how we're going to import it in Node.js. This is pretty important. So the first argument to this dot product function, behind the scenes, like Node.js doesn't, make you do this, but if you're actually writing C code that represents the ones and zeros that Node.js wants, part of that is actually a stateful runtime. So we talked earlier about how, you have inter-process communication. Of course, the processes are stateful, but also even within a single process, there's a sort of stateful environment because Node.js is like a garbage collector, and so does Ruby. They each have their own stateful environments that sort of come along with them. And we'll talk a little bit more about what the implications of that are later. This info function is basically just some like function header info stuff that comes along with Node.js. And then basically, now we're going to start writing C code that represents Ruby stuff. So I've sort of color coded these. Apologies to viewers who can't see different colors, but these yellow ones here are the Node.js thing. So this is stuff coming from the Node API.h. And then these red things are basically the equivalents in Ruby. So now what we're doing here is we're making a Ruby array, calling this RB array new function. And what this is doing is basically it's making the ones and zeros that Ruby expects as a Ruby array, which is pretty cool. Like you don't actually need to literally run Ruby in order to do that. At the end of the day, all the Ruby executable is doing when you run it is it's putting ones and zeros in memory, and C can do exactly the same thing. So when I call this thing, it's making in memory a Ruby array that is completely indistinguishable to Ruby from any other Ruby array. It's just like, yeah, that looks like a Ruby array to me. I assume that was made using Ruby. It's like, no, that was made using C. But you can totally do that. So we're going to make two arrays here. And then basically, I'm not going to show you all this stuff because it's kind of tedious. But at this point, this is where we would sort of convert all the Node arrays to Ruby arrays. I'm not going to walk you through all that because it's kind of involved, but I will show you the return value, and then you can kind of extrapolate to like, okay, once we see how the return value gets converted, which is just one number, you can imagine how that would work in a loop to do the same thing with the arrays. Okay, so here's how we're going to get the answer and convert that. So first, we're going to do this RB fun call. I think you could pronounce this either way. You could say it's fun call, which is clearly what they meant for like function call, or you could say it's func all, which also works. But however you pronounce it, this is where we're going to call the Ruby function. And the first argument, again, is that sort of stateful runtime. So Ruby calls this RBC object, or Node.js called it env, but it's like the garbage collector and all that stuff. And then, of course, we need to tell Ruby the string name of the method we're calling. Because unlike Node.js and Ruby, you always call methods by giving a string for the name of the method. And here we're going to call it the dot product is the string we're going to give it for the method name. And we do have to call this RB intern thing because even the strings are different between Ruby and C. So this is actually converting this C string into a Ruby string so that you can tell Ruby the name of the method that you want to call. Then you have to tell it the number of arguments. And then finally, you actually give it the real arguments that are going to be run by the Ruby method. Okay, cool. And then finally, it's going to return back the Ruby integer, which is this thing right here. And now we need to convert that to Node.js because we're about to return that back to Node. Okay, so in order to do this, we're going to use C as an intermediary. So we're going to go from the Ruby integer to a C integer first. So here's how we're going to do that. We're going to use this num2int thing, which takes the Ruby answer and then converts it into C. That's just something in that ruby.h library that just does this for us. And now that we've got it in C, we basically need to do the same equivalent of take the C integer and convert that into JavaScript using the Node API. So here's how we do that. They call it an API create int 32 for 32-bit integer, and you just give it the existing C answer that we've already got, and then this reference to the JS answer, and it writes it in there. And finally, we can return our JS answer. Okay, so zooming out, we have this function here, which is going to be compiled into something that Node.js can import directly, but it's implemented in C. And what it does is first convert the Node arrays to Ruby arrays, which is a several-step process. So first, we saw creating the two empty Ruby arrays. The part that I left out is that next we would need to iterate over each of the Node arrays that we got in as arguments, convert each of those elements one at a time using that same process that I just did with the C intermediary dance, go from a Node number to a C int, and then take the C int and turn it into a Ruby int, then finally push that Ruby integer onto the Ruby array. Now we finally got two Ruby arrays. We can pass those to Ruby's dot product method, convert its returned Ruby int into a C int, convert that C into a Node number, and return it. Whew, okay, so a lot of stuff going on here. Obviously, this is not a trivial thing to call functions across languages, but we can do it, and we can do it without having to go to the overhead of inter-process communication. But again, you can see there is definitely overhead here, nonetheless. Okay, so at the end of the day, when we are doing this import here from Ruby linear algebra, I said earlier that we're importing it from Ruby. Really, what we're actually importing is actually C. I mean, that was just straight C code the whole way through. It's just that C code is delegating to Ruby behind the scenes as sort of an implementation detail of what that C code is doing. And likewise, when we call this dot product method, what it's literally running is this C function that we just wrote. That's actually what's getting executed. And it happens to be that C function is calling a Ruby method inside of its implementation. But at the end of the day, we got there. We had this goal of calling Ruby from JavaScript inside the same process and getting the answer with no inter-process communication and no network. So as little overhead as we could. Awesome. Okay. But you can imagine that if we wanted to do this with two other languages, we could use the same strategy. This is not limited in any way to Node.js and Ruby. Like, for example, let's say that I wanted to call Ruby from Python. I could totally do that. And in fact, Python also has one of these, they call it a CFFI, which stands for C Foreign Function Interface. FFI is for Foreign Function Interface. It's kind of this general term for calling functions across languages. You can totally just grab this Python library and do exactly the same thing we just did, except instead of the Node.js to C conversions, we would do the same thing, but with Python instead of Node.js. Exactly the same process. And likewise, if you imagine, we could also substitute Ruby for Fortran if we wanted to. Yeah, Fortran, absolutely. Fortran has a CFFI, believe it or not. So you can talk between Fortran and C. And you know why? Because even back in 1957, it was still all ones and zeros. At the end of the day, machine code on punch cards, at the end of the day, what you're specifying is the ones and zeros that need to go in memory, that need to correspond to instructions. And you can still do that today. And C can still put ones and zeros in the right place such that they're understandable as Fortran. That absolutely still works. So really, this kind of works with anything. I mean, any two languages you want to glue together, if you're okay with using C as an intermediary, and then one of them has a CFFI, you can do that. And in fact, even if one of them doesn't have a CFFI, you can write that yourself. It just might take a while and be kind of tedious and error prone, but you can do it. At the end of the day, knowing that computers are just ones and zeros is kind of a superpower. You can really do a lot of stuff that might seem intractable or like sorcery. That certainly was my impression when I first heard about this. I was like, NumPy is using Fortran bindings under the hood? Surely that has to be something like sorcery. Turns out it's not sorcery. It's C. But again, it doesn't have to be C. It could be also Rust. It could be Zig. Like there's definitely different languages that let you do this. Any language where you can sort of manipulate memory directly, you can do the same kind of stuff. It's just, C is a common one that people use. Cool. Okay, so now I did mention that there was some overhead left here, right? When we're doing this C as an intermediary thing, there is definitely some conversion in between these two. Like we had to convert from the Ruby answer that we got from a Ruby number into a C number, and then from a C number into a Node.js number. It would be nicer if we had a num2.js that just went straight from Ruby to JavaScript without the C intermediary. That would be awesome. As far as I know, nobody has done this, but somebody totally could do this if they wanted to, and then we could use it. That's going to be outside the scope of this talk, but just so you're aware, there is a way to do that. But what's even better than that is if you just happen to have the same number representation in the first place. Then you don't need to do any conversion. There's not even a conversion from Ruby to JS. It's just like, oh, the ones and zeros happen to be the same for JavaScript and Ruby. So like, there's just nothing, we can just jump. We're good. All set. So that's the absolute fastest if you wanted to eliminate absolutely all of that overhead between calling the functions across the languages. And this does come up sometimes. So for example, if you've got Rust code calling C code, in some cases like Rust and C integers, certain integers just have exactly the same representation. So you can just be like, yeah, I got it. I got what I need. I'm moving on. But this isn't always the case. Like if, for example, Rust string and C strings, not the same. You cannot just be like, oh, I'll just use the C string as a Rust string and everything's going to be fine. Everything's not going to be fine. So you do kind of need to know like which, when you're going between two languages, which things happen to be the same and which ones happen to be different. In some cases, you might find that absolutely everything that you're trying to do happens to have exactly the same representation. And then there's really no overhead for doing that call. But usually that's not the case. Usually there's some number of differences. In fact, even going back to our talking to Scala calling a Java function example, there's still a whole section of Scala documentation on conversions between Java and Scala collections. So even languages that are designed to be this, at the end of the day, usually languages have differences. That's kind of the reason that you use different languages. They're good at different things and better or worse at certain use cases. And that often comes with different data structures, different in-memory representations, which means that some conversions are usually necessary and kind of unavoidable. Having said that, this is certainly nicer ergonomics than writing all that C code like we did earlier. I would much rather just be like, import this thing, and that's done. That's it. I don't have to do any other work. It's just right there for me. Also, this is much less explosion prone. Like I can sort of trust that the people who did the Scala to Java conversions did that, whereas me writing C code myself, I don't know if that's going to be as nice as something that's sort of been more battle tested and less bespoke like this. Um, Also worth noting, there was a little trick you can do here. So let's say that you're starting from JavaScript and you want to call Ruby, and we're using C data structures as an intermediary. If you don't want to write all that C conversion by hand, like we did earlier with like building up the array and then pushing the stuff on the array and then converting the numbers one at a time, a trick you can do is say, you know what? JavaScript knows how to convert itself into JSON, and Ruby knows how to convert from JSON. So if we're okay with the performance hit, what you can do is say, take JavaScript, turn it into JSON, just give that JSON to C, and then C has a very small amount of work to do to just say, take that JSON and give it to Ruby. That's much less error prone in the sort of C zone where you've got, potentially a lot more errors can happen. So this approach is definitely slower, but it does result in you having to write less C code if you're in a position where you kind of find yourself needing to do that bespoke. Another difference is that when I was calling Java code from Scala, this was all type checked. Now, granted, I mean, in the case of like JavaScript to C to Ruby, JavaScript is not innately type checked, and neither is this sort of like C intermediary. If I added TypeScript on JavaScript and I added sorbet on the Ruby side, that's a type checker for Ruby, the C in the middle would still not be type checked. Like all of this stuff right here, I need to get this right. There's no real like type assistance here because essentially these C bindings just cannot leverage the type definition. C doesn't know about TypeScript. C doesn't know about sorbet. C just knows about the ones and zeros. So when I'm writing this, that can be more error prone, but also at the end of the day, these bindings are not guaranteeing that I'm getting the types right on either side. So if I want to write my TypeScript code and call some sorbet code and ensure that the types match up on both sides, C doesn't help me do that. I need something else that's going to sort of sync up the type definitions separately from syncing up the runtime representations with something like C. Okay, now if I am, let's say, in Rust land and I want to call C++, there actually is a tool, a command line tool, that will help me sync up not only the runtime representations, but also the types at the same time. So this tool is called Rust bindgen, and basically its purpose is to generate Rust type definitions and bindings at the same time, so the types as well as the runtime stuff, from C or C++ type definitions. So I have some existing C++ code base, I've got some type definitions for my C++ code, I just give it to Rust bindgen, and it just generates some Rust files that allow me to just call the C++ directly with typing. Now, I've been working on this programming language called Rock for several years now, and we are trying to sort of generalize this Rust bindgen experience of generating the runtime representation as well as the types in a pretty cool way. So Rock, for those who aren't familiar, its tagline is it wants to be a fast, friendly, functional language. Not really going to get into exactly what Rock is. We're just going to kind of talk about this one aspect of it. But one of the things that's important to us is that Rock is nice to call from other languages. This is like a first-class use case. We want it to be really easy to embed Rock in other languages for all the reasons I mentioned at the start of the talk. So let's, as an example, let's say I've got a Rust code base and I want to call a Rock function from within that Rust code base. So what I can do is I can start by running this command, rock glue, and then I give it a .rock file, which specifies how to convert from Rock types to generated Rust. So basically what this rock glue command will do is use my Rock code's types to generate Rust types and bindings, just like Rust bindgen did starting from C++, except this is starting from Rock instead of from C++. And also this is baked into the Rock compiler. You don't need to get a separate CLI for it. It's just right there in the language. So here's what rock to rust.rock would look like. So basically we have a function called make glue, and it takes as an argument these list of types. So this is essentially a representation that the Rock compiler gives to this function that says, hey, here's all the types of all the functions that you're exposing that Rust could call. Go ahead and just return basically either a list of files that you want to spit out, like the generated Rust files, or else a string of an error that could have happened. So then the implementation of this looks something like this. I'm just going to kind of gloss through this. If you don't know Rock code, that's totally fine. Types.walk shapes, which says like I'm just going to walk over all the different shapes of types that Rock has available. And then we're going to say, let's say that I've got a Rock function here. Here's what I'm going to do here. Here's how I'm going to generate this like Rust code. I'm going to call a function called generate function, which is going to generate the Rust representation of that function, et cetera, et cetera. And I just enumerate all the different types that we've got, like functions and records and tag unions and all that good stuff, lists. And then at the end of the day, there's only about like 10 different types in Rock. So there's not that many different cases to cover. And then we've now generated Rust code for all of those. So let's say that I've implemented my dot product function that we've been talking about this whole time in Rock. Takes two arguments, two arrays of integers, and then it returns an integer. So I just run rock glue rock to Rust, and then basically what it would print out is this. this usually it's best practice to label your generated code as like this was generated. So say generated by rock glue, and then basically this is what it would spit out is here is this Rust function that actually has type annotations on it. Note that the rock one didn't have type annotations. I think this is kind of a cool use case for this because rock has 100% type inference. So like you never have to annotate your types if you don't want to. And so basically, even though this implementation here did not have type annotations on it, rock glue still knows what the types are and it's going to tell you inside this function. And so you can use that to generate the Rust type annotations, which are mandatory in Rust, even though you didn't have to put them in rock. I think that's pretty cool. And then of course, the implementation of this that will be generated by rock glue, it's going to go ahead and call the rock dot product function because Rust is one of those languages that can kind of do the ones and zeros thing itself. You don't need to use C as an intermediary when you're already starting from Rust. Cool. Now, a language where you do actually need to use some sort of intermediary or something like that is JavaScript, as we've seen. So let's say that instead of saying rock glue rock to Rust, I want to say rock glue rock to Node. And somebody has written, that somebody's probably going to be me, let's be honest, writing a way to convert between rock code and JavaScript code, like Node.js code. So here we have exactly the same thing as before. Like there's going to be this make glue function. It's going to take the same list of types in for the same rock program. It's just that this time I'm going to write the implementation so that instead of spitting out Rust code, it's going to spit out Node.js code. Or as we saw earlier, realistically, some combination of Node.js sort of wrapper code and mostly a lot of C code that's going to do the actual heavy lifting of the conversions because Node.js has a way to go from C to working Node.js stuff. And then at the end of the day, I will end up with something that sort of gives me both of those things put together so that inside Node.js, it's going to actually be calling this sort of generated C function instead of writing it by hand. Much nicer to have rock glue generate it. And then it's going to do the conversions. And instead of calling Ruby.product, it'll call the rock.product. And as a bonus, we can also have it spit out TypeScript type definitions because again, make glue just gets all the rock types. So it's like, what's the equivalent of the TypeScript type that we're going to have here? It's like, oh yeah, well, we have a rock string that's going to correspond to a TypeScript string, et cetera. So you can build both the implementation and the type annotations so that if you're using TypeScript rather than JavaScript, as an increasing number of people are, you still get to have your nice type safety when you're calling your rock function. And again, that's even if you don't happen to put any annotations on the rock side. So here's what that TypeScript type definition would look like. Something like this. Again, it's the same sort of input information. It's just that instead of generating a .rust file, it's generating some JS stuff and some TypeScript type definitions. Cool. So at the end of the day, I mean, we had this really nice experience coming from Scala to Java, where I just had to import this Java code and I can just immediately call it and it's type checked and everything's really nice. That was a really great experience. The one downside is that it kind of doesn't generalize. I mean, if you go from Scala to Java, yes, you have this really nice experience. If you go from Scala to Node.js, say, it's a totally different experience. Now you have to get, all this stuff going on that you didn't have to before. But the nice thing about this is that here, we've, after running this one command, ended up with basically the same user experience where it's like, yeah, I just import this thing from here. It's still type checked. It's the same amount of code to import it. Yes, there was some generated code behind the scenes, but I didn't have to write that. I just used this off-the-shelf script that somebody made to convert between Rock and Node, Rock and Rust, Rock and Zig, whatever the two languages are that you want to convert between Rock and. And we've tried to make this as easy as possible, including for the people authoring those conversions, by just building this right into the compiler. So we're sort of trying to get as close as we can to this sort of like holy grail of the nicest experience possible for calling functions across languages so that you can call Rock from other languages really easily. And this works for TypeScript and JavaScript in the same process as fast as possible with the minimal amount of overhead that we can. Yes, there probably in this actual implementation is going to be some C intermediaries, but there doesn't have to be. If somebody wanted to, they really could go all the way to saying this thing is going to implement going straight from TypeScript to Rock if that's what they decided to go with. I should mention that I recently started working at a company called Vendor, and this is something we are literally going to be using at work is TypeScript calling Rock. And the reason we're doing this is because we are interested in migrating from TypeScript to Rock. We have a big TypeScript code base, but we're really big into functional programming. We have a huge Elm front end. So if you're interested in Elm, check us out. And we want to be moving to something more functional on the back end like Rock. And there's a whole bunch of reasons for that that I'm not going to get into here. But basically, the way that we want to do this is incrementally. We don't want to have to sit down and do a big rewrite. How often does that work? But what's much nicer is, hey, what if we could just start importing Rock functions and just start writing them right away? That's the goal, is just to be able to incrementally transition from this legacy technology that we want to move away from, namely TypeScript, towards something we want to be using, which is Rock. And this is a really nice way to do it. By the way, if this sounds interesting, you'd like to come work with me at Vendor, check out this website, vendor.com/careers. But basically, if you're interested in calling functions across languages, we talked about 3 different ways of doing this. So we talked about the network, inter-process communication, and the same process. Now, there are definitely some trade-offs here. So something we didn't really talk about, and just talk through briefly, is going across the network. Look, machines are stateful, right? Servers can be down, network errors can happen. There's deployment timing issues where you can have the wrong version running of different things. Inter-process communication, there's also state across processes. A process can be down. The one process can be running a different version of the binary than you thought it was. Same process doesn't have those problems, but even within the same process, we have these stateful runtimes, right? We have the Node.js runtime. We have the Ruby runtime that has a stateful garbage collector. Actually, Rock is designed to be have a stateless runtime, so you don't have to deal with those problems. But in general, this is something that you typically have to deal with when you're trying to call functions across languages. Now, having said that, we did talk about how same process is the fastest, but one of the trade-offs we didn't talk about is that when you're doing all this C stuff under the hood, like with the ones and zeros, if you mess up and there's an explosion, like we talked about, like getting the numbers wrong, that's going to take out your whole process, which can be really bad if you're trying to do calling functions across languages, for example, for editor extensions. So this is why the language server protocol actually chooses to use inter-process communication, even though there's a bit more overhead compared to doing it in the same process, so that if you have all these extensions and they're all running different languages, some of which might be C or Rust or Zig or languages that can directly manipulate ones and zeros, if one of those messes up and would corrupt memory or would cause a segmentation fault, it doesn't take out the entire editor. It's isolated to that one process. So you see, okay, yes, that stateful process is dead now or has gotten into a bad state, but it's okay. We can recover from that gracefully and just say, hey, your extension crashed, rather than your entire editor just going away. By the way, there's some ways you can do this with WebAssembly. WebAssembly doesn't automatically protect you against these things, but it does give you more control depending on your particular WebAssembly runtime. So that might be an interesting way that you could, in the same process, get some of those same kinds of guarantees. But again, it really depends on the particular WebAssembly runtime you're using. It doesn't automatically protect you from those. Finally, worth noting that the network has some upsides too, which is that, yes, there is definitely some overhead associated with making calls over the network. And if you're just doing a small dot product, I probably would not recommend it. But it is important to note that once you go over the network, you can now distribute whatever your function call is across multiple machines. Like I can now say, I want to make this call to maybe it's gigantic dot product, and I can get a whole fleet of servers working on it. That doesn't really work. It's not available over inter-process communication, or especially not the same process. So again, it's programming. There's lots of trade-offs everywhere. So it's worth knowing and sort of understanding the trade-offs between all these approaches, especially if previously you'd only had one in your toolbox, like going over the network, because it's just so common in everyday programming. Okay, so to sum up everything we talked about, started with, hey, this is a scenario I found myself in so often. This particular task that I'm doing would be a lot easier if I could use it another language to solve it. Maybe I want a library that's another language. Maybe it's in Fortran. Who knows? Maybe I want more performance than I can get here. Like Rock is designed to be quite a high performance language, but if I'm starting from something like Ruby, maybe I want to drop down into another language to give me some extra speed. I want more ergonomics, perhaps, at the expense of speed. I'm writing a bunch of C or C++ code. I'm like, I really would love some Python right here, just to make this a little bit simpler to develop, even at the expense of speed. Or maybe I'm just, like we are at Vendor, trying to incrementally transition languages, and we don't want to have to do it all in one fell swoop and have it be an all or nothing big project that's very risky. We want to do it in a very low risk way and just say, hey, let's just start using a little bit of Rock here, a little bit of Rock there. And then eventually, over time, more and more of a percentage of our code base will become Rock. And then eventually we can just get to the point where we're just using it and enjoying the language that we're using. So now you have some more tools in your toolbox if you want to be calling functions across languages. Thanks very much.